In this video, we're going to use Monte Carlo simulation to illustrate error rates. We're going to use a data set that we used in our first course. These are mouse weights. We have the entire population. We have all the weights from females that are controls. And what we're going to do is we're going to simulate an example where we try 10,000 different diets to see if they have an effect on weight. Now, it's a simulation. And in this case, we're just going to generate them as if the null hypothesis is true for all diets, basically by sampling from the same population, calling 12 of them cases, 12 of them controls, even though we know there's no effect. So this is a case where M is 10,000, the number of tests, and we have M0 is also 10,000 because the null hypothesis is true for all of them. So let's generate that simulation very quickly. And in this case, we can compute R, right? It's just the number of times that the p-values are less than 0.05. That's the procedure we're defining. And now we're going to look at the error rates for this procedure. And we see that in this case that I just ran, I got 399 cases where it's called significant. That's R. And in this case, where I know the null is true for all the tests, this is also V. So V and R are the same thing. Now let's construct a slightly more interesting example where we have 10% of the diets work. So we're going to generate it in a similar way. But now we have 10% of the diets. So for 1,000 diets, there is a difference between the two diets that is 3 grams higher on average. Okay? So we're going to generate that simulation. The null hypothesis, this is what's new here, is a vector that has 9,000 true. The null hypothesis is true, and 1,000 false. The null hypothesis is not true. The alternative is true. Right? So that's how we construct that vector. And now when we create the simulation, when null hypothesis is false, we add delta. That's the difference between cases in control when the diet does have an effect. So that's how we generate alternative hypotheses here. Okay, so that's what this chunk of code does. Let's run that. Okay, and now what we have is we ran 10,000 tests, and for each one we either called it significant or not, but we have another piece of information, and we have that here because we simulate it. We usually don't know when the null hypothesis is true, but here we do. So we can we're going to turn that into a factor, the null hypothesis list, and now we're going to make a table, and here we can see V and S and M1 minus V, all those values from that table we created are here. Right, so we have cases in which the null hypothesis is true, but we call significant, we get 421 false positives. This is V. And then we have cases where the alternative is true and we call significant. This is these are the true positives, right? 520. So we have so now we can start understanding what these error rates are better, and we also are starting to see what the type 2 errors are as well. So we have cases over here that are also errors. This is the alternative is true, but 480 of them we didn't call it significant. So these two are the two type 1 error and then type 1 error and type 2 error. Okay, now let's run. Now this is just one instance. This is really just one simulated value. We run 10,000 tests. We did it once to really see how these are random variables. So to see that V is a random variable. Here V we got 421. We can repeat this experiment over and over and over again, and that value is going to change. So V, that's an important thing to know. V is a random variable. That's why we can talk about the family-wide error rate. What's the probability that V is bigger than 1? Right? That is saying that V is a random variable because we're talking about probability. So we can repeat what we just did 10,000 times and see what happens. So this code is a little bit slow, so I'm going to only do it 10 times. Later we're going to show how we can make this code much faster. But let's run it 10 times, and now I'm going to show you V and S as they happen, right? So here's the first simulation for 10 for V, S is 564, and we can see how they change every time. It's a random variable. So these error rates, that's why we can talk about rates, are defined, we are able to define them because these variables that we had in our error rate table are random variables. So for example, the probability of v being bigger than 1, bigger or equal to 1, which is the family-wise error rate, here it's pretty clear that that probability is going to be very, very high. This procedure has a very high family-wide error rate. Later we're going to see another type of error rate called the false discovery rate, and that will come in a later video.